The name of topic, noise in communication system, subject of the principle of communication. So what is the role of noise in communication system, and what is the disadvantage of noise in communication? So we now here discuss about the noise in detail. And noise in electrical term may be defined as any unwanted introduction of energy tending to interfere with the proper reception and reproduction of transmitted signal, or basically noise is the unwanted signal. So noise is mainly of concern in receiving system where it sets a lower limit on the size of signal that can be usefully received. Even when precautions are taken into eliminate noise from faulty connection or that arising from external source, so it is found that certain fundamental sources of noise are present within electronic equipment or electronic circuit that limit the receiver sensitivity. So this is the uh, one example of the disadvantage of the noise. So we can classify the noise of in different manners. So noise whose source are external to the receiver, and second one is the noise created within the receiver itself. So the role of noise is very disadvantage in the receiver system. Now noise created outside the receiver, external noise can be further classified as atmospheric noise, extraterrestrial noise, and industrial noise. These are the external noise. And atmospheric noise. What is the atmospheric noise? Atmospheric noise or static is generally caused by lighting discharges in thunderstorm and other natural electrical disturbance occurring in the atmosphere. So this is the atmosphere noise. Since these processes are random in nature, it is spread over most of the radio frequency spectrum normally used in broadcasting system. So this atmospheric noise is random process in nature. Atmospheric noise consists of spurious radio signals, or basically noise signals, with components distributed over a wide range of frequencies. It is propagated over the earth in the same way as ordinary radio waves of same frequency, so that at any point on the ground, static will be received from the thunderstorm, local and distant. So atmospheric noise becomes less of frequency above 30 megahertz because of two factors. This is the very high frequency, 30 megahertz. Therefore, the higher frequency are limited to the site of propagation less than 80 kilometer or so. Second one is nature of mechanism generated in this noise is such that very little of it's created in VHF range and above. VH is the very high frequency range, which have the range of 30 megahertz to 300 megahertz frequency. So cosmic noise and solar noise there are two types of noise. So in the solar noise, under normal condition, there is a constant noise radiation from sun simply because it is a large body at a very high temperature, over 6,000 degree centigrade on the surface. It therefore radiates over a very broad frequency spectrum, which include frequency we use for the communication system. Due to constant changing nature of the sun, it undergoes cycle of peak activity from which electrical disturbance erupt, such as corona flares and sunspots. This additional noise produced from a limited portion of the sun, so may be higher magnitude than noise received during period of quiet sun. So this is the solar noise, and next one is the cosmic noise. In cosmic noise, source of cosmic noise are distant stars, as they have high temperature. They radiate RF or radio frequency noise in similar manner as our sun, and their lack in nearness is nearly compensated by their significant number. So the noise received is called black body noise, and the distributed fairly uniformly over the entire sky. So this is the about the cosmic noise. Next one is the industrial noise. In industrial noise, this noise range between 1 to 600 megahertz in urban, suburban, and other industrial area, and it is most prominent. So source of such noise, of industrial noise, automobile and aircraft emissions, electric motors, switching equipments, leakage from high voltage lines, and a multitude of other heavy electrical machines. So these are the source of such industrial noise. The noise is produced by the arc discharge present in all these operations. So this noise is most intense industrial and densely populated area. So this is the about some facts about the industrial noise. Now we come on the internal noise, or we discuss about the internal noise. So in internal noise, noise created by any of the active or passive device found in receiver. So active and passive device, also active device as a diode, transistor, transformer, and passive device is the electronics components such as resistor, capacitor, and inductors. So these devices found in the receiver. So such noise is generally random, impossible to treat on individual voltage basis, but easy to observe that describe statistically because the noise is randomly distributed over the entire radio spectrum. Therefore, it proportional to bandwidth over which it measures. So internal noise can be further classified as in different manners. First one is thermal noise, second one is the snoot noise, and third one is the low frequency or flicker noise. So what is the thermal noise? So thermal noise generated in resistance or capacitance component These are the passive components, and is random and referred as thermal agitation, white or Johnson noise. So these thermal noise also uh, known as white or Johnson noise. What is the causes of thermal noise? So the free electron within a electrical conductor causes kinetic energy as a result of heat exchange between the conductor and its surroundings. Due to this kinetic energy, the electrons are in motion. This motion is randomly through collision with imperfection in the structure of the conductor. This occurs in all real conductors and gives rise to conductors resistance. So this is the cause of second of the thermal noise. Third one, as a result, the electron density throughout the conductor or semiconductor vary randomly, giving rise in randomly vary the voltage across the ends of conductor. So such voltage can be observed as a flicker on a very sensitive voltmeter. Now, the average or mean noise voltage across the conductor is zero, but the root mean square is finite and can be measured. The mean square value of the noise voltage is proportional to the resistance of the conductor, to its absolute temperature, to the frequency bandwidth of the device measured in the noise. So the mean square voltage measure on the meter is found that En square equal to 4k dB, where R is the resistance, K is the Boltzmann constant, and T is the temperature here. And the measurement of thermal noise uh, we can see in this diagram. There is a ideal filter, and here is a source of voltage and resistance, and what is the uh, relation between the transfer function and the noise. And also this is the uh, explanation, and this is the voltage noise, that is the 4 kTBN, where En root mean square noise voltage and R is the resistance of the conductor and T is the temperature in Kelvin. In Bn is the noise bandwidth in Hertz, or uh, bandwidth is the frequency difference of higher frequency minus lower frequency. So is the Bn is the bandwidth in the Hertz. The value of K is Boltzmann constant is the 1.38 into 10 to the power minus 23 joule per Kelvin, and the RMS noise voltage is given by En equal to under root of 4k RTVN. So this is the RMS noise voltage formula. Here we note that thermal noise is not a free source of energy. To abstract the noise power resistance R is to be connected a resistive load, and a thermal equilibrium, the load will supply as much energy to the resistance as it receives. In analogy with any electrical source, the available average power is defined as the maximum average power the source can deliver. Consider a generator of electromagnetic field En volts and internal resistance R. So assuming that RL is noiseless and receiving the maximum noise power generated by the resistance. Under these conditions of maximum power transfer, load resistance must be equal to resistance, then power, noise power Pn equal to V square upon RL or equal to V square upon R, or put the value of V and we find out the value of Pn, En divided by 2 square upon R or equal to En square upon 4R. So this is the noise power Pn equal to Kt Bn, where K is the Boltzmann constant, T is the temperature, and Bn is the bandwidth of the frequency. Now this is the example of calculate the noise voltage. So thermal noise power available from any resistor at room temperature 20 to 90 Kelvin for a bandwidth of 1 megahertz. Calculate also the corresponding noise voltage given that R equal to 50. So for the 1 megahertz bandwidth, the noise power Pn is the calculate by the Pn equal to KTB and formula, and this will be 4 into 10 to the power minus 15 watt. And also we find out the noise voltage En square equal to 4 uh, 4 k tb under root, and put the value of these given parameters and find out the noise voltage, that is the 0.895. So the thermal noise properties of a resistor are maybe represented by the equivalent voltage generator. So equivalent current generator is found using the Norton's theorem using conductance G equal to 1 upon R. So then RMS noise current is given by IN square equal to 4G KTBN. G is the inversely proportional to resistance, or G is the conductance. G equal to 1 upon R. So the noise current is given by this formula In square equal to 4G KTBN. Let R resistance represent the total resistance of the series chain, where R series equal to R1 plus R2 plus R3 and so on. Then the noise voltage of equivalent series resistance is En square equal to 4 RKTBN, and put the value of here series resistance. So the this will be equal to 4 and multiply R1 plus R2 plus R3 and so on KTBN. So En square equal to will be En1 square plus En2 square plus En3 square and so on. Hence the noise voltage of the series chain is given by the En, or equal to under root En1 square plus En2 square and so on. So this is the formula for the noise voltage. And when we take the resistance in series form, what we now we take the resistance in parallel. So with resistance in parallel, it is best to work in terms of conductance. Let conductance represent the parallel combination where G equal to G1 plus G2 plus G3. They are the different conductance. So In square, or noise current, equal to 4G KTBN, and put the value of G here. So this will be equal to 4 G1 plus G2 plus G3 KTBN, and also In square will be equal to In1 square plus In2 square and so on. Next is the reactance. So what is the role of reactance in noise? The reactances do not generate thermal noise. This follows from the fact that reactance cannot dissipate power. So consider an inductive or capacitive reactance. So the reactance may be conductive or may be uh, capacitive, connected in parallel with a resistor R. In thermal equilibrium, equal amount of power must be exchanged. That is P1 equal to P2. What since the reactance cannot dissipate power, the power P2 must be 0 and hence P must also be 0. So this is the role of reactance in the noise. Now we discuss about the shoot noise. So what is the shoot noise? Shoot noise is random fluctuation that generated any direct current crossing potential barriers. The effect occurs because the carriers, electrons and holes in semiconductor do not cross the barrier simultaneously, but rather with random distribution in the timing of each carrier, which gives rise to random component of current superimposed on the steady current. In this case of bipolar junction or BJT, the bias current crossing the forward bias emitter based junction carrier the shoot noise. So in this BJT, the current crossing the forward bias emitter based junction carriers the shoot noise. When amplified, this noise sound as though a shower of lead snow were falling on metal sheet, hence the name is short noise. So this name is short noise. This noise falling on a metal sheet. Although it is always present, short noise is not normally observed during measurement of direct current because it is small compared to however it does contribute significantly to the noise in the system. The mean square noise component is proportional to the DC flowing and most device the mean square shoot noise is given by In square equal to 2 IDC QEBN square ampere, where IDC is the direct current in amperes, Q is the magnitude of the electronic charge, and BN is the equivalent noise bandwidth in hertz. What is the flicker noise or 1 upon F noise? So this noise is observed below frequency of few kilohertz and its spectral density increase with increase in frequency. For this reason, it is sometimes referred to as 1 upon F noise. The cause of flicker noise are not well understood and recognized by its frequency dependence. Flicker noise becomes significant at frequency lower than about 100 Hz. Flicker noise can be reduced significantly by using wire wound or metallic film resistance rather than the more common carbon composition type. In semiconductor, flicker noise arises from fluctuation in the carrier density, holes or electrons, which in turn gave rise to fluctuation in the conductivity of the material. So the noise voltage will be developed whenever direct current flow through the semiconductor and the mean square voltage will be proportional to the square of the direct current. In electronic device, it show up as a how frequency phenomena as the higher frequency overshadowed by white noise from other source. So this is the uh, vehicle noise and or 1 upon f noise. And next, work noise, it consists of sudden step like transition between two or more discrete voltage or current levels as high as several hundred microvolt at random and unpredictable times. Each shift in offset voltage or current often lasts from several milliseconds to second and sound like popcorn popping and hooked up to an audio speaker. The most commonly invoked cause is random tempering and release of charge carriers at thin film interface or at defect sites in bulk semiconductor in crystal. In case where these charge have a significant impact of transistor performance such as underage, a MOS gate or bipolar base region. The output signal can be substantial. These defects can be caused by manufacturing process such as heavily ion implantation. So in this diagram, that is the typical of noise, showing discrete levels of channels, current modulation due to the trapping, spectral density. So the what is the spectral density in terms of noise? Spectral density of power distributed in frequency spectrum it used to differentiate of different type of noise, plot of high intensity or power as a function of frequency or wavelength. So this is the spectral density. So thermal noise lies in category of power signals has spectral density. Bn is property of external receiving system and Bn assume flat. Bn is the bandwidth of the noise from power of noise formula Pn equal to E square n upon 4R or equal to 4 kTBn divided by 4R or equal to kTB. Since En square equal to 4 kTBn, where En RMS noise voltage volt and R equal to resistance of conductor, Bn is the noise bandwidth, K is the Boltzmann constant, which is the value is 1.38 10 to the power minus 23 joule per Kelvin. T is the conductor temperature in Kelvin. So available power spectral density in watts per hertz or joule is GAF equal to Pn upon Bn equal to KT. So this is the formula. Spectral density of mean square voltage is given by GVF equal to E square n upon Vn or equal to 4 kT V square per hertz since E square n equal to 4 kT Vn. Spectral density are flat that is independent of frequency in figure below. So this is the spectral density versus thermal noise spectral density, and this is the diagram which is so the spectral density graph. So thermal noise is also called white noise because of analogy to white light that has flat spectrum means signal contains equal power within a fixed bandwidth at any center frequency. When white noise is passed through a network, then spectral density is changed by shape of network frequency response. So the total noise power at output is sum of the noise contribution over complete frequency range, taking into account of frequency response shape. Consider a power spectral density response in figure. So here in this graph, this is the power spectral density response. At frequency f1 in this figure, the noise power for small bandwidth delta f about f1 is delta pn1 equal to sp f1 delta f here delta f assume flat about f1. So the delta pn1 equal to spectral density in watts per hertz and bandwidth in hertz, or delta pn1 equal to sp f1 dot delta f. So the noise power is equal to area of shaded strip about f1, similar for f2, f3 and so on. That power is sum of all these small areas equal to total area of the curve. Area of curve gives total mean square voltage. So area curve equal to integration of GAF for f equal to 0 to f equal to infinite. So for mean square voltage, SPF1 into delta F equal to SPF1 delta F V square, area of curve gives total mean square voltage. So the next equivalent noise bandwidth. In equivalent noise bandwidth, it is frequency span of noise power curve with amplitude equal to actual peak value and with same integrated area. If R is connected to input of LC filter as in figure A, this represents an input generator of mean square voltage spectral density 4 kT feeding a network of R and LC filter. So the lead transfer function of network including R, VHF, so spectral density for mean square voltage is 4 R kT HF square. HF is the ratio of output to input or transfer function for the voltage of mean square voltage. Here is the transfer versus frequency graph in this diagram. And total mean square output voltage is given by Vn square integration of 4 kT Hf square delta F for F equal to 0 to infinite. So Vn square equal to 4 kT Tx area under Hf whole square curve, or total mean square voltage at the output can be stated as Vn square equal to 4 kT Vn. By above two equations gets equivalent noise bandwidth of network. So the Vn equal to integration of Hf square delta f area under curve of Hf or transfer function square for the frequency from 0 to infinite. So we consider an example in below figure input capacitance of the voltmeter used measure to noise voltage across our circuit diagram. So this is the RC network and transfer function used to determining noise bandwidth in this uh, diagram. So the transfer function of RC network HF equal to 1 upon 1 plus omega CR under root. Equivalent noise bandwidth of the RC network is Bn equal to integration of HF to DF equal to 1 upon 4 RC frequency from 0 to infinite. So Vn square equal to 4kt x1 upon 4 rc equal to 4 equal to kt upon c. So mean square voltage originate from R even though it is independent of R and inversely proportional to C even though C does not generate noise. So transfer function HF equal to XC upon ZS where ZS equal to R into 1 plus J by Q is impedance of the series tuned circuit and XC equal to 1 upon J omega C. So let circuit is resonant at frequency F naught and noise uh, restricted to bandwidth of del F less than F naught about uh, resonant frequency F naught. So transfer function given by the HF equal to 1 upon omega naught and area under HF square curve is small bandwidth. Delta F is the Q square delta F. So mean square noise voltage is Vn square 4RKTBN and Q square R equal to RD and for the frequency of the F0 to infinite and the bandwidth of noise Bn equal to 1 upon 4 RDC. RD is the dynamic resistance of the tuned circuit. Noise bandwidth expressed as a function of 3 decibel bandwidth of the circuit. So the from equation V is the 3 decibel equal to F naught upon Q, RD equal to Q upon omega naught. C combine these equation gets Vn equal to. So the mean square voltage is the output as Vn square equal to 4 RD KTX 1 upon 4 RDC equal to KT upon C where Vn is the bandwidth. So the Vn square equal to 4 RD KT x1 upon 4 RD C equal to KT upon C. Now here assume that Q factor is constant and independent of frequency for end result gives good indication of noise expected in practice but not true for range 0 to infinity. In radio receivers, noise is generated at antenna receiver input and output noise bandwidth is determined by the audio part of the receiver. Equivalent noise bandwidth equal to area of normalized frequency curve for low frequency section. Normalized means curve maximum value is unity. Response curve. So output is decibel related to maximum as in next slide figures. So equivalent noise bandwidth is area of curve for a single sideband type. The noise bandwidth appears on both sides of the carrier and gets doubled. There are different response curve, relative response versus frequency and power ratio versus frequency. There are the noise bandwidth, RF bandwidth, and area curve effective bandwidth under equal to noise. So first curve show the amplifier frequency response curve. B is the curve of a using linear scales, and C is the noise bandwidth of a double sideband receiver. So these are some response curve. Signal to noise ratio S and R. In communication, it is the signal to noise absolute value of noise. It is defined as a power ratio S upon N equal to P S upon Pn or equal to Bn square upon Ps square upon Bn square. So repeater amplifiers insert to make up to the loss in analog telephone cables. If power loss of line section in L, then repeaters amplify power gain G is chosen. So LG equal to 1 long line divided into identical section. In input signal power PS to first section, a signal pass through along the link power output. So each repeater is PS since LG equal to 1 for each link, but noise power are additive. So these are total noise power Pn equal to Pn1 plus Pn2 and so on. So each link are identical and contribute Pn then total noise power. So signal to noise ratio in decibel 10 log of PS upon MPN. So S upon N in decibel. So this is the formula of signal to ratio in decibel, where signal to noise ratio is one link and MdB is no of links expressed as power ratio in decibel. In noise factor is the ratio of available signal to noise ratio at the input to the available signal to noise ratio at the output. So we consider a source of a room temperature is 290 Kelvin providing a input of amplifier. The available noise power from this would be Pn equal to K T naught Bn. So put the value of K equal to Bn equal to equivalent noise bandwidth in Hertz. So there are some available output signal to noise ratio will be less than that at the input, that is represented by in this diagram. So noise factor is defined as the available signal to noise power ratio at the input and signal to noise power ratio at the output. So the noise output power given by the P and naught equal to FG K T naught Bn. So F can be interpreted as the factor by which the amplifier increase the output noise. If amplifier were noiseless, the output noise would be GK T and Bn. So the available output power depend on the actual input power delivered to the amplifier. So we in noise figure, we measure, if we want to measure the noise figure in decibel, so the formula will be 10 log of noise figure. So noise factor is a measured quantity and will be specified for a given amplifier or network. It is usually specified in decibel when it is referred to the as the noise figure. So this is the some examples for calculate the noise figure, and we find out the noise figure with the help of some given data. And amplifier input noise in term of uh, F, amplifier noise is generated in many components throughout the amplifier. What it proves convenient to imagine it to originate from some equivalent power source at the input of the amplifier. The total available power input noise is then P and I equal to P and naught upon G or equal to F K T naught, where uh, power KT naught Bn and hence amplifier must contribute P and A, where P and A equal to F K T naught Bn minus K T naught Bn, so equal to F minus 1 K T naught Bn. So this is the input noise in term of the noise figure F. So this is the examples given here for the noise figure, and we calculate the noise figure with the help of given data. So noise factor of amplifiers in cascade. Cascade means more than one amplifiers are connected in series to each other. So consider first two amplifier in cascade. The problem is to determine the overall noise factor F in terms of individual noise factor and available power gains. The available noise power at output of the amplifier 1 is given by the F1 G1 KT naught V1, and this available to the amplifier 2. So this is the diagram of noise factor of two amplifier in cascade connected. So amplifier 2 has the noise F2 minus F1. So the noise power will be F1 G1 KT naught V n plus F2 minus F1 KT V naught V1 Vn. And so the overall available power of the two amplifier in cascade is G equal to G1 G2, and let over noise factor be F. Then output noise power can also be expressed in as Pn naught equal to F K G T naught Dn, and these are the put the value and lastly find the noise figure and given the and express the noise figure by the formula of F equal to F1 plus F2 minus F1 upon G1. So this equation show the importance of high gain low noise amplifier as the first stage of cascade system. Making G1 large, the noise contribution of the second stage can be made negligible, and F1 must also be small so that noise contribution of the first amplifier is low. So the F equal to noise figure will be F1 plus F2 minus 1 upon G1 plus F2 minus F upon G1 G2. This is known as the noise figure formula. So there are two particular situations where a low noise front end amplifier is employed to reduce the noise. One of these is in satellite receiving system. Two other is in ratio receivers used to pick up big signals such as short wave receivers. So this is the example, some examples of the noise, calculate the noise figure. And next, the noise temperature. The concept of noise temperature is based on available noise power equation Pn equal to KTB Bn. So the concept of applied to an amplifier is related to equivalent noise of the amplifier referred to the input. If the amplifier noise referred to the input is denoted by PNA, so equivalent noise temperature of the amplifier referred to the input T equivalent to PNA upon KBN. So this is the equivalent formula of the temperature T equal to F1 minus 1 upon TA. This shows the proportionality between TE and F. So the equivalent also formula expressed in term of TE1 plus TE2 upon G1 plus TE3 upon G1 G2 plus so on. So this is the for an example of calculate the noise temperature with the help of given data. And these are some reference books: Analog Communication by Bhatt and Rao, and Digital Communication by T.L. Singhal. That is the cover all these topics. And we have some multi-choice questions that is very interesting and important for this topic. Thank you. Thank you very much.